thank you very much for the introduction. Thanks a lot to organizers from and Tobias Suki for inviting me here. It's a great workshop. So the presentation is about ultrafast THz magnetometry, and it's about how to measure very minute and very fast changes in magnetization state of your material using Terahertz emission spectroscopy. So from Terahertz emission spectroscopy, if you do everything correctly, you can determine by how many millitesla and how many picoseconds your magnetization in sample changes. So this work was done in our group, it's Physics group in Bielefeld, and mostly by this fine gentleman, Wentao Zhang. So it was part of his PhD project. So I'll be repeating many of the slides that were already shown, but please bear with me, it all makes sense. Yeah? You'll see it at the end. So what drives Terahertz radiation? There's two ways to describe the emission of light. One is the dipole-out transitions between quantum levels. Another one is this classical Hertz dipole, where you basically create the polarization or electric dipole, or it can be magnetic dipole, and then you change the dipole moment in time, and it will emit. So we will be looking at this classical picture of light emission in this talk. And this classical light emission is the basis of Terahertz emission spectroscopy. This is the method that exists since late 90s already. And the basic idea is that you have an interesting sample, and then you can impulsively excite the sample with a laser pulse, with Terahertz pulse, with anything else. And then this excitation can lead to the change of dielectric polarization or magnetization in your sample. And then this change in time domain of polarization and magnetization will become the source of its own Terahertz emission, of its own electromagnetic emission. And if this change happens on picosecond or sub-picosecond time scale, then this electromagnetic emission is Terahertz. And then you coherently detect it, best with free space electro-optic sampling. And then in principle, you can reconstruct what you detect as electro-optic signal back to polarization or magnetization dynamics in your sample in a contact-free manner. There's two types of emission that we can look at, the electric dipole and magnetic dipole radiation. So here, those are this famous 2 times derivative in time of polarization or magnetization, but I already Fourier transform it for you into the frequency domain. So this is the Fourier representation of this 2 times derivative formulas that everybody knows. And they're only valid for the point source if you look right on axis of the emission. Only then it will be 2 times derivative. So for the general case, it's much more complicated. Yeah? So there's 2 possible sources of emission, electric or magnetic dipole, and both of them will then contribute to your detectable, the electro-optic signal. And this electro-optic signal can, in principle, but only in principle, be rigorously reconstructed to those sources. So this is what is scientifically interesting, right? So the polarization or magnetization dynamics in the material. So this ultrafast Terahertz magnetometry is this magnetic version of Terahertz emission spectroscopy that allows you to reconstruct your electro-optic sampling signal back to ultrafast magnetization in your sample in a calibrated manner. So you will know by how many millitesla and how many picoseconds, for example, a piece of iron will demagnetize if you hit it with a laser pulse. If you speak about ultrafast magnetism, you need to speak about this man, of course, Eric Boriper. So that's Eric visiting my group when we were still actually based around here in Mainz, and Eric has still had 4 years to live. And Eric is, of course, most known for this pioneering experiment of ultrafast demagnetization dynamics. So what they did back then was an optical pump probe, optical pump Moki probe, and the sample was a nickel nanofilm. They hit it with a short laser pulse, and then they observed very, very fast demagnetization, which was a very interesting observation, because back then people thought, okay, magnetization is a slow process, and the natural time scale would be the ferromagnetic resonance time scale, which is gigahertz. Yeah? And here they observed the sub-picosecond magnetization change, and they tried to fit the spin temperature and electronic temperature, spin temperature, lattice temperature, and came up with such a dynamics of electron temperature, for example, in this experiment. Yeah? So what we have here, we have a very fast change of macroscopic magnetic moment that was detected in all optical spectroscopy. And then the next logical step would be just to use this change of magnetization in time as a source of Terahertz emission. Yeah? And short time afterwards, Eric Boriper with another big Terahertz scientist, Charlie Schmutmeyer, who also left us fairly recently, they did this experiment. So they, again, used the nickel film. This time it was capped by chromium, hit it with a short laser pulse, and it indeed emitted terahertz. And then, back then, in 2004, the explanation was that this is the direct terahertz emission from transient demagnetization. So you demagnetize iron, you have the time-dependent change of microscopic magnetization, and then a very, very simple naive picture, you can basically integrate this detected terahertz, or this field, 2 times, and then you will arrive at the magnetization dynamics in your sample. So that was the interpretation back then, 2004. Importantly, like all of you already know, especially at the end of this workshop, that you can have the electromagnetic terahertz emission from your sample that will be spin-related or magnetic in its core, but the mechanism will be the electric dipole. So basically, there will be some spin dynamics that will then lead to normal conduction current, like in wires, that will then emit terahertz radiation. And so here we owe our understanding to this fine young gentleman, Tobias Kampfrat, and his colleagues from 2013. And this is this modern-day terahertz spintronic emitter technology. So if you have a piece of ferromagnetic metal, you hit it with a laser pulse, then you will create the spin-polarized conduction current perpendicular to the film. It will not emit any terahertz. But then if you will, so the reason for this spin-polarized current is mode scattering. So the mobility of spin-up and spin-down electrons is different, and also different band velocities for the excited spin-up and spin-down electrons. And then if you inject the spin-polarized current into the heavy metal, it will start seeing the spin-orbit coupling, leading to a reverse spin-Hall effect. And then this spin current will be converted to the perpendicularly propagated normal, very boring conduction current that will finally emit the terahertz. So bottom line, you all know this, of course, yeah? So the bottom line here, spin-polarized electrons move, you get the terahertz emission via electric dipole mechanism. So this thing emits by the exact same mechanism as photoconductor switch as a semiconductor terahertz emitter. Even though the basic physics behind the terahertz emission is hot spin dynamics. So this slide you've seen many, many times. So this is the super optimized spintronic terahertz emitter that Tom is now selling, and everybody should buy at least one. And this is this bilayer, non-optimized. It looks like a flat line, but there's a little bit of signal in there, so it's not total zero. Yeah, so basically, it's just an emission from such a bilayer. You have a ferromagnet, and then you have a non-magnetic metal. Well, so when the electrons can diffuse, and then you'll be seeing a little bit of terahertz. And this is the comparison of spintronic emission with classical terahertz technology, like nonlinear crystals. Yeah? So let's remember this seemingly flat line. Yeah, there's a very, very tiny signal there that has originated from spin-orbit coupling from inverse spin-Hall effect in the bilayer. So let's go back to Eric Boris-Paire and Charlie Schmutt, my work. So in the original Ultrafast DMAG paper by Eric Boris-Paire, it was a nickel nanofilm sandwiched between 2 dielectrics. It was grown on glass, or deposited on glass, and was capped with a dielectric with magnesium difluoride. And the sample that they used for the terahertz emission experiment was capped with chromium, which is a metal, yeah? Which is non-magnetic metal. And now our understanding of this result, so after Tobias' work, is that this pulse has mostly originated from inverse spin-Hall effect, from coupling of electrons from nickel, spin-polarized electron from nickel into the chromium, and converting the spin current into conduction current. So this is not the signal originating from the transient demagnetization, not from this dynamics. And the question is, can you still observe transient demagnetization, pure transient demagnetization, in terahertz emission experiment? Can you do it in a calibrated manner? And what can you learn from it? So this is what this talk is all about. Yeah. So now we know that moving spin-polarized electrons will most likely cause inverse spin-Hall effect and electric dipole emission like in spintronic emitters. So the idea is, if you want to observe the pure transient demagnetization dynamics, you should not let electrons move. There should be zero net spin-polarized current in the material. And also, different symmetries associated with different effects involved, and from the symmetries you can then exclude different contributions to your Terahertz emission. So using clever sample design and Terahertz emission symmetry, it should be possible to really observe the pure transient demagnetization in Terahertz emission. So this work was done, so Tobias was part of this cooperation, but we started this actually with Eric Boripé when he visited us, and the samples came from his group. So Guy Schmerbe and Jacek Arabski, they were his colleagues who have grown the samples for this experiment. And we had two types of samples. We had the sample with diffusion barriers. It was a thin 10 nanometer thick iron film grown on MGO and then capped with MGO. And if you photoexcite 10 nanometer iron film with 800 nanometer light, then because of multiple interference of your laser light, you will have uniform excitation profile in this film. Yeah, so basically, you will not have any gradient of hot electrons there. The film will be excited uniformly, so there will be no diffusion even within the film. And in the second sample was capped with palladium, so it's metallic cap. So if you photoexcite this first sample with diffusion barriers, there will be zero net spin polarized current in the film. But if you excite the second sample with the metal capping, it is like a spintronic bilayer. Spin polarized electrons will enter palladium, and then this current can be then converted into conduction current, leading to electric dipole radiation, like in spintronic technology. Yeah? So we think we understand this process very well, and this is what we would like to observe now. Let's start with the sample where the electrons can actually move. So you apply magnetic field, so you force magnetization to be in a known direction here. And then you hit the sample with a laser pulse, inducing the spin polarized current. Now it's in negative directions from iron back into palladium. And this is the formula for conduction current via inverse spin Hall effect, which is proportionality sign. So it's the spin Hall angle times spin current cross product with magnetization. Yeah? So those two are the vectors, and the product will also be the vector. And now we can play with symmetries. Yeah? So here, now we have the spin current in negative direction and magnetization in this direction. That produces terahertz. We detect terahertz coherently with electro-optic sampling, and then we basically save the time trace. Now we change the direction of magnetic field here. Now we change the sign of this vector here, and now we see that the terahertz emission also flipped its sign. So clearly this terahertz emission is then related to the magnetic order in the sample. But there's one more knob that we can now tune. We can flip the sample and play with the direction of the spin current with JS here. Yeah? So we now flip the sample without flipping the magnetic field. So now the conduction current will be pointing, spin polarized current will be pointing in the opposite direction. And we also now see the flip of the sign. Yeah? So the symmetry of this measurement fully supports that the terahertz emission comes predominantly from inverse spin Hall effect. This we know from the symmetries on magnetic field, on magnetic ordering, and the direction of the spin current. Now, the interesting sample, the sample where the electrons actually cannot move. So we apply a magnetic field, hit it with a laser pulse, we get terahertz emission, and we save the trace. And now we will flip the magnetic field, and then we see that the detected terahertz trace also flipped its sign. So obviously, this terahertz emission then has relation to magnetic ordering in your sample. And then for sanity check, we flip the sample, and then we didn't see any flip of the terahertz emission. So the difference in amplitude is because of different outcouplings, terahertz outcouplings in this scenario. Yeah? So basically, in this case, the terahertz emission is only related to the magnetic order in the sample, but not to the direction of where the electrons could move. But, well, we know that they cannot move in this film. So from this sample, we should then indeed expect the terahertz emission via pure transient demagnetization process. So now this is a good sample. Now let's see which process is stronger. Yeah, so we have the terahertz emission via inverse spin Hall effect, where the electrons can move and then coupled to the conduction current, and the sample where the electrons where the magnetization just quenches globally everywhere, also leading to terahertz emission. So this is the relative strength of those two effects. So if the electrons can move, you will have 10 times stronger terahertz emission than when the electrons cannot move. So the contribution of pure magnetic quench in laser excited magnetic film is mega, super tiny, giga tiny. So you can totally ignore it. So if you give electron space to move, your observations will be inverse pinhole effect and the terahertz radiation via electric dipole radiation. And this is a non-optimized terahertz spintronic emitter. It's just two layers we did without any thinking of optimizing terahertz emission. So let's go back to this almost flat line. So this would correspond to this situation. Yeah? So this is terahertz bilayer spintronic emitter without any optimization. It gives very, very weak emission compared to optimized spintronic emitter or to nonlinear crystals. And the terahertz emission via pure magnetic quench is even 10 times weaker than this. So it's a very, very weak process. So you really need to have very stable lab in order to be able to observe. It's a super, super tiny signal. But by measuring it carefully, you can actually learn a lot. So, but first you need to reconstruct what you measure, your observable electro-optic signal, back to the magnetization dynamics in your sample. And your observable is EOS, so electro-optic signal. So this is why you should not try to use photoconductive detection in terahertz emission spectroscopy, because photoconductive detection is not calibrated. Whereas the electro-optic sampling can be totally calibrated to incoming terahertz field. So from electro-optic signal, you can really come back to the field incident in the detector in absolute values, basically how many volts per centimeter per how many femtoseconds is hitting your detector. Okay. And this is the interesting quantity that we want to figure out, the magnetization dynamics, but it is now convoluted with the transfer function from the emission to here. And this transfer function includes the outcoupling of the dipole emission, the whole beam path in your spectrometer, electro-optic detection, non-ideality in alignment, and. So it's a very, very complicated transfer function. And if you do not deconvolute this transfer function correctly from your electro-optic signal, you will arrive at wrong transient magnetization curve. Yeah? So that has to be done very, very rigorously. So we looked into math behind all that, and we wrote this paper a couple of years back, where we really analyze all the influences in terahertz emission spectroscopy. So we consider the electric dipole and magnetic dipole emission. We look at the effects of misalignment of spectrometer. And then we basically established that the best spectrometer configuration for terahertz emission spectroscopy is line of sight spectrometer without any focusing in the middle. And you should come with a large and collimated pump beam, so that your terahertz emission will also come as a more or less collimated beam with very weak divergence. And then the reconstruction will include the least error, so to speak. And what also helps is that you can also use a reference emitter that you know very well, for example, well-known nonlinear crystal like zinc telluride. You can theoretically calculate what happens to the polarization zinc telluride if you know the parameters of your laser pulse. And then you can compare it with electro-optic sampling. This is how you can actually determine the transfer function from emitter to the detector experimentally. Okay. So lots of math, but it's not complicated, but all the equations are there. Just please have a look at this paper. So now we are ready to come to final results, finally. So this is now electro-optic signal from optically excited iron and detected in the far field. So it's super, super tiny signal. So it took lots of averaging. And now we apply the math, and we reconstruct this observable terahertz electro-optic signal to the magnetization dynamics in the sample in a calibrated manner. Yeah, so electro-optic signal is calibrated. It's delta V over V is dimensionless. And now if we know the transfer function, we know by how many millitesla in how many picoseconds iron has demagnetized. So it's not a proportionality. It's really calibrated result. So what we see here, we have the very fast demagnetization of iron. So the effective magnetic field in iron is 2.15 Tesla, and we demagnetize it by 15 millitesla by heating with, I think it was 1 millijoule per square centimeter of 800 nanometer light. So this increases the spin temperature, as Tobias has explained to us, that creates spin voltage, that demagnetizes the iron, and then the iron remagnetizes again. Yeah, this is transient demagnetization, very well known. And now we also have this thing. Yeah, so if you're into Terahertz pulses, then you will realize that this feature actually is encoded by this and this wiggle in the electro-optic signal. Yeah. And it's not noise, it's a real thing. Yeah, so the noise is this. So the rest is actually it's a real thing. So this thing is a magnetoelastic contribution to transient demagnetization of your sample. So if you hit any metal with a laser pulse, it will get hot, it will expand. So speed of sound, this is the speed of expansion, is few nanometers per picosecond. And your film is few nanometers thick. So this expansion will result in a picosecond timescale acoustic phonon pulse. You'll have two halves, so you'll have half of this acoustic phonon pulse going to the substrate, which is semi-infinite, you'll never see it again. Another half will leave the iron, will go into the cap layer, which is thin. We'll get full reflection at the interface between condensed matter and vacuum, 100% reflection. Will come back into the iron, and now there's a pressure wave moving into your iron and moving atomic planes. And these atomic planes will be moved now, and the exchange interaction iron will be weakened, and this will lead to additional demagnetization channel in your iron. Yeah? So now in the signal, we see two contributions to ultrafast demag, so hot magnons, well understood, and on top of that, slightly time delayed, the acoustic demagnetization of iron. And I remind you that this signal is super mega tiny. Yeah? But if you measure it correctly and reconstruct it correctly, you get all this info, which is wonderful. So we had very nice theory collaboration with Peter Opinier and Pablo Maldonado in Uppsala. And we gave them the parameters of the sample and then the parameters of our laser pulse, nothing else, and asked them to reconstruct the demagnetization or to compute the demagnetization from their first principle calculations. And they came up with this dashed curve. So all the features are more or less nicely reproduced. Well, there's a little bit of kink here in the magnetoelastic contribution, but qualitatively everything is there. So this is now the calculation. So this is the pure transient demag contribution, and this is the strain in the iron film that then couples via spin phonon coupling to the spin system and then demagnetizes or modulates the magnetization in the iron film on top of that. So now this is the entirety of our data. So here we used different pump fluences from 0.25 to 1 millijoule per square centimeter of 800 nanometer light, and we see that the stronger we pump, the stronger it demagnetizes. We always see this acoustic contribution, and this is the calculation, or first principle calculation by Peter Opinier and Pablo Maldonado, and we see that the order of magnitude is always the same. So it's not a fit of the data to the models, first principle calculations. And all the key features and the timing is captured very, very reliably. So what we noticed in the data is this constant 7-to-1 ratio between the hot magnon and the acoustic demagnetization amplitudes for all the fluences that we have used. That brings me to the end. In summary, we have demonstrated the Terahertz emission by pure transient demagnetization, I think for the first time. And we could separate it from electric dipole contribution. If you want to observe pure demag signal, you should not let those electrons move. You should really make sure that there's no diffusion of spin polarized electrons in the sample, else it will lead to spin orbit coupling and much stronger electric dipole Terahertz emission that will obscure everything that you would like to observe. And I think also to the first time we have observed the magnetoelastic contribution on the same in the same signal, in the same experiment as the hot magnon. So those are the publications, and thank you very much for your attention.